This section is on static electricity and charge. Along with mass, time, distance, temperature, and brightness, charge is one of the fundamental physical quantities we will encounter this semester. Other physical quantities are typically composed of these. There are two types of charge, positive and negative. Positive charges are commonly carried by protons, negative charges by electrons. That's what we'll see this semester. There are other types of charged particles, but we won't discuss them. The principle of conservation of charge states that the total amount of charge in a closed system is conserved. And so however much your closed system starts with is how much it ends with. In SI units, charge is measured in coulombs. That's our SI unit for charge. 1 coulomb is the charge on 6.25 times 10 to the 18th protons. So 1 proton has a charge of 1 coulomb divided by this big number. So 1 over 6.25 times 10 to the 18th is 1.6 times 10 to the minus 19th coulombs, and that's the charge on a proton. The charge on an electron is just the negative of that, or a negative 1.6 times 10 to the minus 19th coulombs. Electrons and protons carry exactly the opposite charge of each other. And then we define the quantity E, and that's just the charge on a proton, even though it looks like an electron, just like we represent G as positive 9.8 meters per second squared, even though gravity is downward, we represent E as the charge on a proton. It's 1.6 times 10 to the minus 19th coulombs, and so the charge on a proton is E, and the charge on an electron is minus E. Their respective masses, the mass of a proton is 1.67 times 10 to the negative 27 kilograms, and the mass on an electron is 9.11 times 10 to the minus 31 kilograms, almost 2,000 times less than the proton. Electrons and protons, even though they aren't the only charge carriers in the universe, they're the ones we encounter most commonly, and so they're the ones we'll deal with. In most materials, the electrons are the objects that are moving, flowing if we have charge flow, and the protons are stationary in the nucleus. Materials that allow charges to flow easily are called conductors. These are typically metals, and those that resist charge flow are called insulators, and they're typically nonmetals. The fundamental force between electrical charges is shown by Coulomb's law. Coulomb's law is named after Charles Coulomb, who was a French physicist who lived from 1736 to 1806. Coulomb's law was discovered as a law between charged particles that's very similar to Newton's law of gravitation between particles that have mass. Newton's law of gravitation looks like this. The force of gravity is equal to G times m1 m2 over r squared, where G is the universal gravitational constant, m1 and m2 are two masses, and r is the distance between them. Coulomb's law looks like this. We can call it F Coulomb if we want, usually just F. It's K Q1 Q2 over r squared, where again K is a constant, Q1 and Q2 are the two charges, and r is the distance between the two objects. Charles Coulomb, when he was looking for a force that acted between charged particles, he could tell by looking at static electricity on a comb or something like that there were forces that acted. He first tried a form that looked just like Newton's law, because he thought if Newton's law worked for masses, a very similar form might work for charges. In this case, the constant K is also a universal constant, just like G was, and it's 9 times 10 to the 9th Newton meters squared per Coulomb squared. That's the units for this K, right? Q1 and Q2 are the charges, and R is the distance between them. Notice that just like with Coulomb's law, if we double the distance between two charges, the force gets weaker by 4 times. Because if we double the distance, the r squared makes that a 4, and we get a force that's 4 times weaker. There are a few other things to notice. If, unlike with mass, charges can be positive or negative. And so since we know that opposites attract, if the total sign of the force is negative, that means that one of these is positive and one of these is negative, because k is positive and r squared is always positive. So if the force is negative, then it's an attractive force. If the force is positive, that is to say if both Q1 and Q2 are positive, or both Q1 and Q2 are negative, then this force comes out positive and the force is repulsive. So notice now that if we double the distance between the charges, that is to say we make r twice as big, the force gets 4 times smaller, because just like with gravity, there's an r squared in the denominator, and so if we double the distance, the force gets 4 times smaller. If the force is negative, right, that means that the charges Q1 and Q2 had opposite signs, and therefore the force is attractive. So if the force is negative between two charges, that means it's attractive. If the force is positive, that means that the charges had the same sign, that is to say they were either both positive or both negative, and the force is repulsive. So now we can try to work a problem. We can say, what is the electrical force between a proton and an electron in a hydrogen atom? And so first we have to figure out some of the basic parameters for this problem. We already know that the charge for a proton is 1.6 times 10 to the minus 19th coulombs, and that the charge on an electron is minus 1.6 times 10 to the minus 19th coulombs. In this problem, we're going to assume an average distance between the electron and the proton, and for those in a hydrogen atom, it's about 10 to the minus 10 meters. And so now we just need to plug these in and solve. We have the force is equal to k q proton q electron over r squared, right? And that's equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared times the charge on a proton, which is 1.6 times 10 to the minus 19th coulombs, right, times the charge on an electron, which is minus 1.6 times 10 to the minus 19th coulombs, right, all divided by the distance squared, which is 10 to the minus 10 meters squared. And if we evaluate that, what we get is about minus 2.3 times 10 to the minus 8th newtons. The minus sign here means that the two charges were opposite. I'm multiplying a negative charge by a positive charge, and so that produces a negative number here, which tells me that the force is attractive. And the rest of the number, the 2.3 times 10 to the minus 8, tells me how large it is. I don't really have a context for how big this number is, but I can compare it to something else that might give me a better idea of whether this is big or small. So now I want to answer the question, what is the gravitational force between an electron and a proton in a hydrogen atom, so I can compare the value of the electrical force that I got on the last sheet and see if it has see if it's significantly different from the gravitational force, a force that we're already a little bit familiar with. And so I can write down the formula for the gravitational force. It's just G, mass of the proton, mass of the electron, over r squared, where r is the distance between them. And we just said a few pages back that the mass of the proton is 1.67 times 10 to the negative 27 kilograms, and the mass of the electron is 9.11 times 10 to the minus 31 kilograms. Again, their separation is 10 to the minus 10 meters. And so now all I have to do is kind of plug in just like I did before, and I can say, well, the gravitational force between them is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. That's my G, right? And then I multiply that by the two masses, which is 1.67 times 10 to the negative 27 kilograms times 9.11 times 10 to the minus 31 kilograms. I'm running out of room. Right. Let me fix that a little bit. There we go. All divided by 10 to the minus 10 meters squared. Right. And so when I evaluate that, I get about 1 times 10 to the minus 47 newtons. Notice in the previous problem, I had the Coulomb force. There's the gravitational force. The Coulomb force was minus 2.3 times 10 to the minus 8th newtons, right? So this number is almost 10 to the 40th times bigger than the gravitational number. The electrical force totally dominates. We would have to have 40 more digits of this number for this one to have any significance at all. This has 46 zeros before the 1. And so we'd have to have a whole bunch of zeros out here before the significance of the gravitational force showed up. And that's why when you hear about chemical reactions in chemistry, they never talk about the gravitational force.